Okay, what about removing files? So you've got a file now, you know how to move them around or rename them. To remove them, the command is rm, right? It's short for remove. Now, what you need to remember is that in Unix, right, file deletion is effectively permanent, right? There is no reliable way to completely recover the contents of an undeleted file, right? So what happens when you remove a file is that the data that's associated with the file, right? So remember, the inode tells Unix where the contents of the file are actually located on disk, right? The inode itself is not, the data on disk is not necessarily overwritten when you remove the file, right? So in principle, if you know where the contents of the file are on your disk, you can go back and recover the contents, right? The problem is that the way Unix works is that even if there's only one user on the computer, the operating system's doing stuff as well. So as the operating is doing stuff as well, it might choose to overwrite the part of your disk that contains the information belonging to your file because it's doing some other work and it needs some disk space for something. So there's no guaranteed way to recover the contents of the deleted file, right? There are tools that you can purchase or download that will attempt to recover the contents of a file, but none of this stuff is guaranteed to work, right? It's considered to be one of the flaws of the original design of Unix, right? It's not surprising. So remember back when Unix was developed in the 70s, permanent storage was extraordinarily expensive, right? So we think of permanent storage, so your disk now is quite cheap, right? But back in the day, whatever corresponds to a disk turned out to be extremely expensive. And so it kind of made sense that you don't want to, that you'd want to reuse any quote unquote disk space if it was no longer needed. So if you remove a file, it immediately became, the contents of the file on disk immediately became available for being overwritten. It wasn't a disk back when Unix was created. It was something else, right? But unfortunately, that still is true today, right? So if you want to remove one or more files, rm and then the file name, right? These are regular files only, right? And again, you can use wildcards to specify groups of files, right? So here I'm going to, looks like I'm going to make a bunch of files. Okay, so we got a bunch of files: a text, b text, c text, d text, capital A text, right? I can remove a text and b text by asking rm to remove those files, right? So run that, right? Notice a text and b text are now gone, right? You can remove all of the files ending with .txt using star.txt, right? Or star.txt if you want to remove the files that end with the extension txt, right? So, bloop, right? Notice that all the other files are now gone, right? Also notice that word starting with A is now in red, right? So what this thing here was what's called a soft link. So it was a soft link to the file a.text, right? And so all a soft link is, it's just another name for a file, right? That's all a soft link is, right? So if I remove the file that word starting with A was pointing at, right? Then it's called a dangling link now, right? Because it now points at nothing, right? So that's why it's showing you this in red, right? It's trying to indicate to you that this link is no longer valid, right? It doesn't remove the link, right? So this name still exists. It's just this name refers to nothing now. Right. If you want to, again, you can use -i for the interactive prompt, right? And it'll ask you, do you want to remove this file? Yes or no. Do you want to remove this file? Yes or no, and so on and so on and so forth. Right. Okay, rm will not remove a directory unless you tell it otherwise, right? If you want to remove an empty directory, there's a special command for that, right? So rmdir, whoops, sorry, will remove an empty directory, right? So if I make a directory sumdir, there's sumdir, right? So I just made it so there's nothing in it, right? It's empty, so I can remove it using rmdir, right? So it's gone now, right? If you try to remove a directory and there's something in it, there's a file or directories in that directory, rmdir won't do it for you. Right? So here, I'm going to make a directory, sumdir. Right? I'm going to create the file sumfile inside sumdir, and then I'm going to try to remove sumdir. Right? So make dir, rmdir now complains. Right? It says the directory is not empty. Right? So it turns out rmdir, I don't think it will anyway. Let's see what it does. Man, rmdir. Okay, I'm going to check to see if it can actually remove a non, oh, here. So the answer is no, right? Remove the directory or directories if they are empty, right? So if you have multiple empty directories, you can remove the multiple empty directories with one invocation of rmdir. I just wanted to know if there's a way to remove a non-empty directory, and the answer is no. Okay, so what if you do want to remove a non-empty directory? Because there's lots of cases where you've made a directory, it's got a bunch of files in it, you don't care about them anymore, you'd like to get rid of everything. Right? It would be terrible to have to individually remove all the files and then remove the directory. Right? So rm has a flag -r that will recursively remove the contents of a directory. Right? Now remember, rm won't ask you by default, right? Do you want to remove this stuff? So it will really remove everything. Right? So recursively remove the contents of sumdir. Let me go in and fiddle with sumdir just to show you. So where is it? Okay, so I'm going to go into sumdir. There's one file in it. Right? I'm going to make a directory. I'm going to make a bunch of directories. X, Y, Z. And then I'm going to put something in Z. Some file. Oops, drat. Dutch, Z, some file. Sorry, touch, X, Y, Z, some file. There we go. All right. So there's X. Inside X, there's Y. And inside Y, there's Z. And finally, inside Z, there is some file. Right? So I'm going to go up one directory. Sorry. ls. Okay, so I would like to remove that directory and everything that's inside of it. Right? So rm -r, sumdir. Right? Recursively remove some directory and all of its contents. Right? It disappears. It doesn't say, are you sure? Right? It doesn't ask you anything. It's gone. Right? Sumdir is gone. And all the files and directories inside of sumdir are also gone. Right? And there's no way that I can get them back at this point in time. Okay, so you have to be, so when you're doing your assignments, right, and you're playing around with these commands, right, be very careful about what you're doing, right? They will overwrite existing files. Remove will remove existing files without asking you, right? So it's possible while you're working on assignment 2 or assignment 3 or 4, 5, or 6, and you're practicing your Unix commands, that you remove all of your assignment directories. Right? Or you remove all of the files in your current assignment directory. There's no way for you to get them back. Right? So be very careful when you're using rm, mv, and cp. Right? They will overwrite existing files for you. If you're a system administrator, so if you're someone who has root permissions, right? Whatever you do, do not go into the root. Oh, sorry. Do not go into the root directory. Right, remember, the root directory is where is the start of all the directories on your system, and do rm -r*. Right? Recursively remove everything in this directory, so that will delete your entire file system if you have the permissions to do so. Right? And really, whatever you do, don't put the F in. Right? The F means force. So if you try to remove a file and you don't have permission, if you try to remove a file and you don't have write permission on that directory, right, rm will normally complain. But if you force it to, you can override the permissions and actually delete the file. Right? So that'll blow up your file system, which will more or less crash your system, and now your entire file system is gone. So don't do that. If you go on the internet and search for removing the root directory, you'll find all kinds of horror stories from system administrators when they've done this to a running production system. That's not good. Someone did that with, I think, Toy Story. So the first version of Toy Story, so the way they rendered that, it was rendered on Unix workstations. Someone nuked the entire directory containing all of the assets. And so it was gone. There was no backups either for it. And so the only reason they didn't have to recreate everything from scratch or go bankrupt was because someone had copied everything onto their home computer. And so there was, someone had a slightly older copy of all the files. Okay, so you can Google that too if you're interested in that. So Pixar almost met with disaster because someone did RM something somewhere they shouldn't have. Okay, so CP will copy files. So you can copy a file onto a new file. So make a separate copy of the file with a different name, right? You can make a separate copy of the file in a different directory, right? Or you can copy a bunch of files into one directory, right? But like MV, you can't copy a bunch of files into a bunch of different directories, or copy a bunch of files onto a bunch of different file names, right? All right, so CP works more or less the same as MV, right? If I'd like to make a copy of the file having that name, right, you just write copy source file, destination file, right? If the destination file exists, copy will overwrite the destination file, right? So here I've got, oh wait, this is not gonna work because I deleted all these files. Where am I? 2024 notes, bash. Okay, so I don't have, I guess this, I didn't proofread this notebook carefully enough. Okay, I need to make a text in awords.text. Sorry, a.text. Is that right? Yes. Okay, so I have a file called a.text. Let me put something in it. Aardvark, apple, and. So a bunch of words starting with A, right? If I'd like to make a copy of that file, right, you just say which file you want to copy, right, and what would you like its name to be, right? So I think it's what did I call it? A words. Like that, right? And now you've got a copy of a.text. So it's important here what the word copy means, right? If you're taking 124, you know that copy doesn't always mean copy. So it turns out there really is, on your disk, right, a copy of the contents of a.text, and there is in a separate place on your disk, right, there exists the contents of awords.text, right? So there really is a full-blown copy of these two files. Right, so if you look in a.text, that's the contents, and if you look in awords.text, the contents are there, right? If I change the contents of a.text, right, the contents of this file do not change, right? So they really do exist separately on your disk. Right. If you've got a bunch of files that you would like to copy somewhere else, right, into another directory, you can do so, right? So I can copy all of the files that start with uppercase A and end in txt, and I can make a copy of those and in dir1. Oops, sorry. So copy a*text into dir1, right? Now, copy doesn't affect the original files, so they're both here, right? If I look in dir1 though, there's a.text and awords.text, and if you look at their contents, dir1 a*, right? So all the files starting with A, right? You can see there's the contents of a.text, there's the contents of awords.text, right? So there's now 4 copies of the same file on my disk now, right? You can copy directories if you'd like, and their contents using -r. So again, this is recursive, right? So recursively the contents of dir1, right, into a new directory called words, right? You don't have to copy to an existing directory, right? You can copy will make a copy of dir1 and save that copy in the directory words. So cp-r, right? Like that, right? And there's now a directory called words, right? If you look inside words, right, there's an a.text, an awords.text, a c file, and a z file. So there's now 6 copies of whatever was in a.text, right? All right, linking to files. I'm going to skip this section here. You can read about it if you're interested in this. I'm not going to ask you about this in this course. If you're using Unix or Linux at all on a regular basis, you probably want to read this because Unix uses linking a lot. But I don't think it's important that you know this in this course. So if you want to take a look at the rest of the contents of the rest of the notebook, I won't ask you about it on any of the tests. And I won't ask you to use it on any of your assignments. But it's here if you need to find out about it. All right, permissions. So Unix or Unix-like operating systems, they were originally designed for multitasking, multi-user systems. So multitasking means more than one thing is running on the computer at a time, or at least the illusion of the more than one thing is running on the computer at a time. Multi-user means there are multiple users accessing the same computer at a time. That's not the way most of you use your computers at home, right? Most of you, it's single user, right? Multitasking, but single user. Right. Many of the early computers that ran Unix, they were meant for multiple users at a time. Right. Now, if you have a bunch of people using the same computer at a time, right, it's probably a good idea that each individual user has some control over their own files. Right. So I shouldn't be able to look at your files, for example, on a multi-user system. Right. You shouldn't be able to look at my files. Unless we grant each other special permission, right? Similarly, it's probably a good idea that you and I can't look at the special operating system files, right? So it's probably a good idea if I can't go into the root directory and delete the entire root directory, right? Because that'll blow up your entire operating system. And so Unix introduced this idea of permissions on files, right? Or access rights, if you want to call them that. So in Unix, there are three separate groups of people, users, sorry. There's a group called user, right? So that, there's a person called user, right? There's a user called user. The user is the owner of a file, right? So every file in Unix has a username associated with it, right? When I run ls in my command, in my shell, with the -l option, right? That name there is the user of the file, right? Of the owner of the file. Okay. There's also something called a group, right? And so every user belongs to a group, and a file also belongs to a group, or groups, I think. Is that true? I don't remember. Anyway, multiple users can belong to a group. So you can group different users into things called groups, right? And every user belongs to at least one group. Modern Linux distributions will create a group having the same name as the user whenever you add a new user to the system, right? So here, that second Burton is the group associated with that file, right? That group has the same name as my username. So groups, to create a group, you have to have system administrator privileges. We're not really going to create groups in this course, right? But if you want to know anything about system administration, if you want to learn about system administration, or if you learn about system administration, you will eventually come across this notion of groups and how to create them, right? We're not going to create them here. And then finally, there is this group called other, right? So any user that's part of other, so not an owner or not part of the group associated with the file, falls in the class other. Okay, I gotta run that. Okay, gonna run that. Great. And then I'm gonna run that. Okay. So when I run that command with the -l option, I get a bunch of information, right? And so that information that it's showing you there, the part that we're interested in really is this stuff here for this notebook. Right? So that stuff there tells you the permissions that are associated with this file, right? So the first hyphen is the file type, right? So the file type, in this case, it's a hyphen, so that means it's a regular file, right? The next three characters So rw hyphen are the permissions that the user has for this file. Right? So the user is me, right? The R means I can read this file. The W means I can write to this file. The hyphen means I cannot execute this file, or in other words, I cannot run this file like it were a regular program or a regular command. Right? So read, write, execute permission. The next three are the permissions for the group. Right? So anybody part of the group Burton can read the file. Right? They cannot write to the file, and they cannot, oops, sorry, it's really awkward highlighting stuff in Markdown, in Jupyter. And they cannot run the file as though it were a regular program. And then the next three are the permissions that belong to everybody else, right? So everybody who's not me and everybody that's not part of my group, right? They can't do anything with the file. So they can't read it, they can't write to it, and they can't run it like a regular program. The notebook tells you about the other parts of this output. You can read the notebook if you want to know what these are. But it's the permissions I'm interested in here, right? So the permissions are the leftmost symbols in the output of ls, right? Okay, so the first symbol that's output is the file type, right? And there are 7 standard file types in Unix, right? And so those are the 1, 2, 3. These are the 5. This is showing you 5 of them. So these are some of the ones that you might see if you're poking around on your file system, right? For most of you, you're only going to see the hyphen, right? So the first character is a hyphen, that means it's a regular file. If the first character is a D, it's a directory, right? Unless you're poking around your operating system files, you probably won't see L, C, or B in this course. If you want to know what they are though, there they are. And you can look those up if you want to know more information about them, right? So hyphen and D, regular file, directory. The remaining permissions indicate the user group and other permissions for the file, right? And so what I just explained in the previous example, right? So R means read permission is on, W means write permission is on. If there is an X, that means execute permission is on. Do I have anything that's executable? The dir name is probably, oh, sorry. But, okay, so that directory does in fact have execute, so I have execute permission on that directory, my group has execute permission on that directory, and everybody else also has execute permission on that directory. Okay, so permissions affect regular files and directories differently, right? So if you have a regular file and you have read permission on that file, right, that means you can open that file and read its contents. Right. If you have write permission on a file, that means you can write to the file, right? Or the file can be truncated. So in other words, you can delete the contents of the file, but you cannot delete the file itself, right? So that's weird, right? So write permission, I can modify the file, but I can't actually remove it, right? Similarly, you can't create or rename the file, right? So just having write permission does not guarantee that you can actually do anything with its file name. Finally, execute means you can run the program or execute it. Run the file as though it were a program or command, or execute it as though it were a script. Okay, now the permissions mean something different if you're talking about directories. If you have read permission on a directory, then you can list the contents of the directory, right? As long as you also have execute permission on the directory as well, right? So execute permission on the directory means that you can go into the directory, right? So you can switch into that directory. So cd, that directory name will work, right? To read the directory, you need both read and execute permission on that directory name, right? Write permission on the directory means you can create files, I can delete files, and I can rename files in the directory as long as I also have execute permission on that directory. Okay, so the command that you want to use is chmod. So I guess it's change mode or something like that is what it's short for. So that's the thing that you would use to change the permissions of a file. If you just want to look at the permissions on a file, you can use ls with the long output format option. There is another way to get the permissions of the file. There's a command called stat, S-T-A-T, that you can use to get information about files. So stat's quite powerful. It will tell you permissions, file size, when was the file last accessed, when was it modified, and so on and so on and so forth. In other words, it gives you, it will reveal information about the inode belonging to a file. All right, so permissions as octal values. So when you use ls minus l, you get the permissions with the letters R, W, and X, right? Another way to think about this is that you can think of the permissions as being either on or off, right? So you either have read permission or you don't, you either have write permission or you don't, or you have execute permission or you don't. So they are essentially binary values, right? 0 or 1. 0 meaning you don't have that permission, 1 meaning you do have that permission. So you can write the permissions as 3-bit binary values, right? 0, 0, 0 means you have none of the permissions, right? So in binary, you would write that as 0, 0, 0, right? In decimal, that's just the value 0, right? But in the octal format, so octal is base 8, right? So in base 8, that number 0 is also 0, right? So remember in base 8, you're going to count from 0 through 7, right? And then when you add 1 to 7, you go back to 0, right? Just like in base 10, when you have 9 and add 1, you go to 0, right? And in binary, when you have 1 and add 1 to it, you also go to 0, right? So if you change, so octal turns out to be sort of common in computing. So base 8 numbers are often useful. Base 16 numbers are also very useful. So that's hexadecimal. And of course, decimal and binary are also very common. All right, so if you consider the number 001 in binary, right, you can imagine that that means you have execute permission on the file, but no other permissions, right? In octal, 001 is just 1, right? And if you go down the list, right, you're just going up in value by 1 each time. So 0, 1, 2, 3, 4, 5, 6, 7 corresponds to these binary values, right? And if you look over here, you can see what the permissions correspond to, right? Anywhere there's a 1, you have that permission. Anywhere there's a 0, you don't have that permission. Right, and so using the octal value, so a value between 0 and 7, you can specify the permissions that belong to a to either the user, the group, or the owner, or everybody else. Sorry. Right, now the problem is that you have to remember this mapping. 0 is easy, right? No permissions. 7 is easy, all permissions. Everything else becomes a little bit harder, right? And some of these permissions, if you look at them, they don't really make sense, right? So here's a file that has execute permission on it, but you can't read or write it. So that doesn't sound very useful, right? If this, it has execute permission, so this suggests that it's a runnable program, right? But to run the program, you need to be able to read the file, and you don't have read permission on it. So this combination of permissions seems nonsensical, right? Here's another one. You can write the file, but you can't read or execute on it, right? So technically it's possible, you can write to the file, right? But you can't actually read the contents of the file. So probably less useful, right? Not super useful. WX is similar, right? R makes sense, you can read the file, but you can't do anything else with it. RX makes sense, RW, no execute makes sense, RWX makes sense, right? So some of these are less commonly used than others. Okay, so what you do is you use 3 octal values to specify the permissions for the user, then the group, and then the everybody else. So 400 means user has read permission. The 0 means group has no permissions, and the final 0 means everybody else has no permissions, right? So remember, it's always user, then the group, then everybody else. Right, and then you specify the file or files whose permissions you want to change. So you can change the permissions of multiple files at a time. Right, so if we run that code there, and we look at file 1, we see that its permissions are in fact, so the user has, sorry, can I do this? Yes, the user has only read permission, right? Group has no permissions, so that's the second 0, that's the first 0, and, oops, sorry, and everybody else, that's the second 0, have no permissions, right? If you want everybody to have access, read access on the file, right, you can do that, right? So 444, everybody gets read access, and you can see here, everybody has read access. Right? And finally, 755, so 7 means the user has all permissions, right? Group has read permission, and everybody else has read permissions. You can use 755. Sorry, 5 is read and R and X, right? Yes, read and execute, right? So there we go. So the user has all permissions, right? Group has only read and execute, and everybody else has read and execute. Right, so if you can remember the octal values, this is the easiest way to use change permissions on a file. Right? Now, if you're not often changing permissions on files, and most users are not often changing permissions on files, it's probably easier to use the symbolic form. Right? So R, W, and X, that's easy to understand, right? Read, write, execute. U, G, and O, user or owner group. O is other, A is everybody. Right? So you can combine one or more of these symbols, and then combine that with R, W, and X to specify the permissions. So for example, you also need to say what you want to do with the permissions. So you can add a permission, you can remove a permission with minus, right? And you can use the assignment, so equals, to say the permission is this, right? So add, remove, and equals. All right, so there's take away all permissions on file 1, right, using an octal code, right? We see that there's no permissions. Right? If I want everybody to read the file, I can write A plus R, right? So A for all, right, plus add R read permission. You can also use A equals R here if you wanted to, right? That says set the, so plus means set the read permission if it's not already there, right? If read permission is already there, it does nothing. Right? A equals R means set the permission of set the read permission for everybody to R, right? To read. So there's a subtle difference between plus and equals. Right? And so now you can see everybody has read permission on the file. Right? If you want to add write permission now to the file as well, right? For the user, so you, for the user, give them write permission. Right? We see the user now has read and write permission. Everybody else, unchanged. Right? If you want to remove a permission from user, group, or other, you use the minus. So U minus W says, for the user, remove write permission. Right? And now you can see that the user is missing their write permission now. Right? Assignment will set all of the permissions on, right, that you specify. So U equals RWX will set read, write, and execute permission, like that, right? U equals, U equals nothing will strip all the permissions, right? And so you can see here the user has no permissions now, right? Notice that it doesn't affect group or other here, right? So you're saying the permissions for the user are nothing, right? The permissions for the user are everything, right? The permission for the user is just read, it's just write, right? Sorry, it's read and write. This is just write, and so on and so forth. Well, RWX, right? Yeah.
Is there a difference between like plus and equals? I think you just said that.
Yeah, there is a difference. So when you assign the permissions, right? So let's do, let's give everybody the permissions like that. Oh, sorry. Okay, so the user has all permissions, right? Now if I do U equals R, right? It strips the W and the X, right? So this is assignment of permissions. I think it's supposed to be that, right? Okay. Now you can change the permissions for everybody, or for the group and everybody, or sorry, for the user and the group. Basically for multiple different users on your system using the comma, right? So if I want to change group's permission to R and X, so read and execute, right? And I want to take away all permissions from everybody else, right? I can use G equals RX, then a comma, and then O minus RWX. So remove read, write, and execute permission for everybody else. Right? And there you can see, so the user has, the user has whatever permissions that they had from before, right? Group now changes to R and X, right? And everybody else has no permissions now, right? And so you can combine, if you wanted to, you can specify everything. You can be overly specific, right? So if you wanted to, you could do something like U plus R, R, like that, right? In this case, it's going to do nothing. The user already has read permission, right? So you're going to get the exact same thing, right? And you can also do multiple files at a time. So, and including directories, right? So a directory is just a file. So if I wanted to, I can change the permissions of both file1 and temp to whatever that is, right? So notice here, here, the directory temp has those permissions right now, right? If I run this code, you'll see they change, right? So they change to whatever, they change to these permissions right here, right? The same as file1, right? Now what you can't do is you can't have two different files and have different permissions at the same time, right? So you can set multiple files to all have the same permissions, right? If you want to change the permissions on multiple files to different permissions, you have to do it one at a time.